4.5 Indeterminate Forms and L'Hopital's Rule. The outline of this video is as follows. We will begin by exploring what happens when evaluating a limit produces a meaningless expression, which we call an indeterminate form. I will then introduce a powerful technique called L'Hopital's Rule, which uses derivatives to find limits that we cannot otherwise determine. We will first apply this rule to the most common indeterminate fractions, the 0 over 0 form and the infinity over infinity form. From there, we will learn how to algebraically manipulate other tricky forms, like infinity times 0 or infinity minus infinity, to get them into a fractional form where the rule applies. To finish, we will tackle the most complex cases, the indeterminate powers such as 1 to the power of infinity, by using logarithms to transform the problem into one we can solve with L'Hopital's rule. Let us begin by exploring a common challenge in calculus: evaluating limits that do not give a clear answer from direct substitution. This situation arises when we encounter what are called indeterminate forms. For instance, if we look at the function defined as the fraction with x minus sin x in the numerator and x cubed in the denominator, a problem emerges as x approaches 0. Both the top and the bottom of this fraction also approach 0, leading to the expression 0 over 0. This is called an indeterminate form because we cannot determine the limit from this form alone. Do not assume the limit is simply 0 or that it does not exist. Other common indeterminate forms that we will investigate include infinity over infinity, infinity minus infinity, and 0 to the power of 0. The essential point to remember is that an indeterminate form is a signal that we need a more powerful method to find the true limit. Here is a powerful tool for finding limits called L'Hopital's rule, which helps us solve the indeterminate form 0 over 0. The theorem states that if we need to find the limit of a fraction, f of x over g of x, as x approaches a value a, and both f of a and g of a equal 0, we can try a different approach. As long as the functions are differentiable and the derivative of the denominator is not 0, the original limit is equal to the limit of a new fraction, the derivative of f of x divided by the derivative of g of x. A crucial warning is to not confuse this with the quotient rule. You are not taking the derivative of the entire fraction, but rather the derivatives of the numerator and denominator separately. In short, this rule let us replace a difficult 0 over 0 limit with a potentially much simpler one by comparing how fast the top and bottom functions are changing. Let us walk through two more examples to build our intuition for applying L'Hopital's rule. First, consider the limit as x approaches 0 of the quantity 3 x minus sine x, all divided by x. Direct substitution gives us 0 over 0, which is the indeterminate form we need. So, we take the derivative of the numerator, which is 3 minus cosine x, and the derivative of the denominator, which is 1. Evaluating this new limit as x approaches 0 gives us 3 minus 1, which is 2. In the second example, the limit of the quantity the square root of 1 plus x minus 1 all over x, we again get 0 over 0. Applying the rule, the derivative of the top is 1 over the quantity 2 times the square root of 1 plus x, and the bottom's derivative is just 1. Plugging in 0 gives a final answer of 1/2. Remember to differentiate the numerator and denominator separately, and do not use the quotient rule. The key is to transform a difficult limit into a simpler one that you can evaluate directly. Sometimes, applying L'Hopital's rule once is not enough to resolve an indeterminate form, and in these cases, we can apply the rule repeatedly. The process is straightforward. After you apply the rule, you check the new limit. If it is still an indeterminate form like 0 over 0, you simply apply the rule again to the new fraction of derivatives. For example, to find the limit of the quantity x minus sine x all over x cubed, we first get 1 minus cosine x over 3x squared. This is still 0 over 0, so we apply the rule again to get sine x over 6x. One more application gives us cosine x over 6, which evaluates to 1/6 as x approaches 0. You can continue this process as many times as needed, but you must stop as soon as the limit is no longer indeterminate. The main takeaway is that repeated application is a powerful tool for more complex limits. It is crucial to know when to stop applying L'Hopital's rule, as applying it incorrectly leads to the wrong answer. The correct procedure is to continue differentiating the numerator and the denominator as long as you still have an indeterminate 0 over 0 form. You must stop differentiating as soon as the new limit is no longer indeterminate. For example, consider the limit as x approaches 0 of the fraction with numerator 1 minus cosine of x, and denominator x plus x squared. Applying the rule once gives us the limit of sine of x over the quantity 1 plus 2x. If we substitute 0 into this new expression, we get 0 over 1, which equals 0. A limit is found. It is a common mistake to apply the rule again here, but since the form is no longer indeterminate, doing so would incorrectly give an answer of 1/2. Therefore, always check that the limit is still an indeterminate form before each differentiation step. L'Hopital's rule is also a powerful tool for evaluating one-sided limits, which is essential when a function behaves differently as it approaches a point from the left versus the right. Let us examine the function sign of x over x squared as x approaches 0 from the positive side. This gives us the indeterminate form 0 over 0, so we can apply the rule. The derivative of the numerator is cosine of x, and the derivative of the denominator is 2x. As x gets closer to 0 from the right, cosine of x approaches 1, while 2x approaches 0 through small positive numbers, which means the limit is positive infinity. Now for the left-hand limit, the setup is the same. After applying the rule, we again have cosine of x over 2x. The numerator still approaches 1, but this time the denominator approaches 0 through small negative numbers, resulting in a limit of negative infinity. Because the left and right-hand limits do not agree, the overall two-sided limit does not exist. L'Hopital's rule also provides a powerful way to handle limits involving the indeterminate form infinity over infinity. The principle is exactly the same as before. If both the numerator and denominator of a fraction approach infinity, the limit of that fraction is the same as the limit of the fraction of their derivatives. For example, let us find the limit of e to the power x over x squared as x approaches infinity. This is an infinity over infinity form, so we apply the rule and get the limit of e to the power x over 2x. Since this is still an infinity over infinity form, we can simply apply the rule again. This gives us the limit of e to the power x over 2, which clearly goes to infinity. The important lesson here is that you can apply L'Hopital's rule repeatedly as long as you continue to get an indeterminate form. L'Hopital's rule also works for the indeterminate forms infinity times 0 and infinity minus infinity, but only after you first rewrite the expression as a fraction. For a form like infinity times 0, such as the limit of the square root of x times the natural log of x, we can transform it into a fraction. By rewriting the expression as the natural log of x, divided by the quantity 1 over the square root of x, we now have an infinity over infinity form, which the rule shows has a limit of 0. Similarly, for an infinity minus infinity form, like the limit of 1 over sine x minus 1 over x, the key is to first combine the terms over a common denominator. This gives us the fraction x minus sine x, all over the quantity x times sine x, which is a 0 over 0 form. The essential technique is to use algebra to convert these expressions into a standard fraction before applying the rule. Now let us see how to solve limits involving indeterminate power forms which arise when a function's base and exponent both approach challenging values. These forms are 1 to the power of infinity, 0 to the power of 0, and infinity to the power of 0. The key is to use logarithms to transform the problem into a fraction. First, we set a variable y equal to our function and take its natural logarithm, which turns the exponent into a simple multiplier. We can then apply L'Hopital's rule to find the limit of this logarithmic expression. For example, with the function the quantity 1 plus x, all to the power of 1 over x, the limit of its natural logarithm as x approaches 0 is 1. The crucial final step is to remember to exponentiate this result. The original limit is e raised to that power. So the final answer is e to the power of 1, which is simply e. Let us work through another indeterminate power, this time the form infinity to the power of 0, which we can solve using the same logarithm method as before. We want to find the limit of the function x to the power of 1 over x as x approaches infinity. This is an indeterminate form because a huge number raised to a power approaching 0 is not obvious. To solve it, we first find the limit of the natural logarithm of the function, which simplifies to the fraction natural log of x over x. As x approaches infinity, this gives us the indeterminate form infinity over infinity, so we can apply L'Hopital's rule. The derivative of the numerator is 1 over x, and the derivative of the denominator is 1, so the limit of this new fraction is 0. Remember, this is the limit of the logarithm, not our final answer. To find the original limit, we must exponentiate this result, giving us e to the power of 0. Therefore, the limit of x to the power of 1 over x as x approaches infinity is 1. To build an intuition for why L'Hopital's rule works, we can look at a special case where our functions are well behaved and approach 0. The key idea is that if you zoom in very close to a point on a smooth function, it becomes nearly indistinguishable from its tangent line. This is called linearization. So, for x values near a, we can approximate f of x with its tangent line equation, f prime of a times the quantity x minus a. Likewise, g of x is approximately g prime of a times the same quantity. When we take the limit of the fraction f of x over g of x, we can substitute these linear approximations. The term x minus a then cancels from both the top and bottom, leaving just the fraction f prime of a over g prime of a kms. This demonstrates that the limit of the ratio of the functions becomes the limit of the ratio of their derivatives. Now we will look at Cauchy's mean value theorem, a powerful generalization of the standard mean value theorem that applies to a pair of functions. It begins with two functions, f and g, that are continuous over a closed interval from a to b and differentiable on the open interval between them. We add one more important condition. The derivative of g must never be 0 inside that interval. The theorem then guarantees that there is some point c within the interval where the ratio of the derivatives, f prime of c over g prime of c, exactly equals the ratio of the total changes in the functions, which is the quantity f of b minus f of a, all divided by the quantity g of b minus g of a. To see how this connects to what we know, imagine if the function g of x is simply x. Its derivative is just 1, and the equation becomes the standard mean value theorem, where f prime of c equals the slope of the secant line. The essential idea is that this theorem relates the ratio of two instantaneous rates of change to the ratio of their average rates of change. Cauchy's mean value theorem has a powerful geometric interpretation that makes the formula much easier to understand. Imagine a curve in the plane defined parametrically, where the x position is g of t and the y position is f of t. First, if we draw a straight line connecting the curve's start and end points, we create a secant line, and its slope is given by the fraction f of b minus f of a over g of b minus g of a. Next, at any point on the curve, the slope of the tangent line is the ratio of the derivatives f prime of t over g prime of t. Cauchy's theorem simply guarantees that there is at least one point somewhere along that curve where the tangent line is perfectly parallel to the secant line. In other words, the instantaneous slope at some point C must equal the average slope across the entire interval. Let us wrap up our discussion by summarizing how to use L'Hopital's rule, which is our systematic method for evaluating limits that result in an indeterminate form. The core idea applies directly to the forms 0 over 0 and infinity over infinity, where the limit of a fraction equals the limit of the fraction of its derivatives. For other indeterminate forms, like infinity times 0 or infinity minus infinity, you must first perform an algebraic manipulation to convert the expression into a proper 0 over 0 or infinity over infinity fraction. When you encounter indeterminate powers, such as 1 to the power of infinity or 0 to the power of 0, the crucial first step is to take the natural logarithm. Finally, remember that the formal proof for this powerful technique relies on Cauchy's mean value theorem. In short, L'Hopital's rule uses derivatives to find the value of limits that are not immediately obvious. This is a great point to pause and check our understanding of when and how to apply L'Hopital's rule. For the first question, consider the limit of the quantity x squared plus 1 over the quantity x plus 1 as x approaches 1. If we directly substitute 1 for x, the numerator becomes 2, and the denominator also becomes 2. The result is simply 1, which is a well-defined number, not an indeterminate form like 0 over 0. Therefore, L'Hopital's rule is not applicable here. The second question reminds us to think about other forms, like infinity times 0. In those cases, you must first perform an algebraic conversion to create a fraction before you can apply the rule. Always remember to check for an indeterminate form first. That is the essential condition for using this tool.